All right, so this is a walkthrough that I've been wanting to do for a little while here, and that is about how backpropagation actually works in code. So let's just set things up here. We're doing a simple linear regression, which will have enough of the basic ideas of how to do backprop that we'll be able to see how it works. So to set this up, I'm just going to have a single feature, x, and a continuous outcome variable, y. Later on, we can generalize this to lots of features and lots of outputs that aren't just numbers, different kinds of loss functions, all that stuff. Let's make sure we understand the basics here. So what I just did here is a kind of fancy way to generate a random noise data set that has some outliers. So we'll be able to see the difference between mean squared error and mean absolute error. So what I did here is to set up this problem, I'm saying here's the prediction task we're going to do. We're going to try to fit a line that looks like slope times x, whatever x value is, plus our bias or intercept. And that's going to be our prediction. So we'll scatter plot the true values and then plot our prediction. So we'll get this value here. And then I'm going to compute the mean squared error and mean absolute error by just taking the residual or the error and either squaring it or taking its absolute value and taking the mean of the result. So what you can see here is an interactive widget that will let us just try playing around with the slope and the bias to see if we can get a good mean squared error or mean absolute error. Let's just look at the mean squared error right now. So 4.3, 4.30, 32. Okay, so that looks like the bias that minimizes our mean squared error. Now I can go over to the slope and see if I can get better than that. I'm just looking at the MSE value and I see 4.2968. That's probably pretty good. Let me see if I can go back to the bias and get any better. 4.286. Okay, so that was a little bit better. Okay, now I'm at 2.8. I wonder if I can get better by increasing the slope a little bit. 4.28, 2.7. Oh, yes, I can. Oh, so 2.7. So we can go back and forth a little bit and just kind of manually adjust these two things one at a time and see if we can find the best value of slope and bias to minimize mean squared error. Then we can go again and do that for minimizing the mean absolute error, and that might end up with a different value because, for example, this line is getting pulled down a lot by the point way down here. So the minimum mean absolute error will be able to pull up the slope and get a better mean absolute error because it fits more of the rest of the points there. So, but wouldn't it be nice if we could do this automatically? So instead of having to wiggle these knobs and sliders by hand, we could just let the computer do it. And maybe it's a little frustrating wiggling knobs and sliders if there's two of them. Imagine 2 gigabytes worth of knobs and sliders, billions of them. So that would be untenable. So let's get our computer to do what a computer's good at. So to start this off, what I'm going to do is use PyTorch. Ignore this for a moment. I'll get right back to it. So I'm going to say that our slope and bias are both constants right now, but I'm going to put them inside of a tensor, which will allow us to save that value and also track what its gradient is. So we have slope and bias both starting out at 0. For real neural net settings, we would want to start them out at like random initializations, but for this simple task, 0 will work fine enough for now. And then let's go through one step at a time. Let me rewrite this whole thing just so that we can see exactly what's going on. So I'm going to take the length of the input as our x, and I'm going to make a prediction by taking our slope times x plus our bias. Now what I want to do is draw this at the same time. So over here, I'm going to say what we've got is some kind of a vector x, and I'm going to have a slope. I'm going to call it w for reasons that you'll see sometime too. And this, I'm going to first combine them to say I'm going to do w times x. And we'll build these up to more complicated things later, but for now we just have this single multiplication operation, which we can think of as taking the two inputs to this thing and multiplying them. And then we're going to take the going to take the result of this and put it into a add. We're going to add the bias. Okay, so now we've got this thing, which we call our y predicted. So this is w times x, and this is w times x plus b, or slope times x plus bias. So now we're going to try to compute the error. So let me start with the diagram this time, and then we can switch back. So one of our inputs over here was this, this value x, but we also get what the true value was for each one of these x's. So what we're going to do is compute our error by subtracting. We're going to subtract the true value from the prediction, so we get our error is true minus predicted coming out of this. So let's write that in code. Let me just first show what ypred looks like. So our prediction looks like a bunch of zeros because, well, our slope was 0, so we're doing 0 times x, so 0 plus 0 for bias. So a whole bunch of zeros. It's always instructive to look at the shape. So there are 100 of them because we made 100 random x values for our x values here. So there are 100. Our length of x was 100 points here. So we get 100 predictions, and each one of them was wrong by some amount. So we take our y true minus y predicted. Let's look at our error here. So we've got a bunch of errors. How many of them? Well, there better be 100 of them, one for each. Yeah, there you go, 100 errors. So what do we do with the errors? Well, we want to take them and let's compute the mean absolute error, just because the gradient will look really nice for that. Well, I can take mean absolute error as one line, but let's break it up into separate lines, and we'll see why in a moment. So I'm going to take the absolute error, and take our error, and just call abs on it. So now what does absolute error look like? Well, it's all the same things, except all the negative values got flipped over to positive. So what's that look like? Let's just draw, like, there's this absolute value operator here, and now we get out the absolute error, and that's just the absolute value of error. And all of these operations are happening element-wise. So y true and y pred are both 100 numbers, but when we subtract them like this, that just means take each number in y true and subtract the corresponding number in y pred, or take each number in error and take its absolute value. So now we have the absolute error, and now I'm going to sum all those errors. So that's the summation sign. So we're just going to say our sum absolute error is sum of our absolute errors. Or you could write it this way if you could write the mathy summation sign if you want with absolute errors. Okay, so we're going to get our sum absolute error out of there, and then just to shortcut a little bit, we're going to divide by n to get our mean absolute error is sum absolute error over n. Okay, so now we just do that in code. And we have sum absolute error equals absolute error dot sum. And that better be a single number. Yep, it is. And now we take that and divide by n to get the mean absolute error. And that better be a single number also. So now we ask, so we get a mean absolute error here, 1.6. We could do better than that. We can get 1.2. How would we change slope and bias so that we can get a better mean absolute error than that? So what we can do, let me delete this because I just wrote this. I'm gonna skip this for a moment here. I'm gonna tell our mean absolute, no, I actually do want that. Internal detail here, but then I'm going to tell PyTorch to push this to propagate backwards, what change could we make to slope or bias to change the mean absolute error? That just did a bunch of stuff under the hood, and what it gives us is, well, let's just look at bias, and now let's look at slope. So what we now get is a slope.grad. That's saying, this number says that when we change slope by 1 wiggle, then mean absolute error goes down by 1/5 of a wiggle. So I'm speaking approximately in the sense that we'll make concrete in a moment here. But that means that if I were to take this slope and I'm going to push it down, so actually I want the mean absolute error to go down, so I want to push slope up because that'll make the mean absolute error go down. That's what that means. So I'm going to go up by, let's just say 0.001, and that means that I'm going to expect the mean absolute error. Now let's just go up by 0.01. So I'm going to expect the mean absolute error to change by 0.01 times that. So I'm going to expect it to go down by 0.024. So instead of seeing 1.607.6, I should see 1.605.4 or something like that. Let's just try that. Well, I need to rerun this, don't I? 1.6052. Okay, so it wasn't quite exactly, because this was a linearized approximation. Because the gradient is only applicable exactly right where the original function was evaluated, sort of approximating this overall input-output function by a flat plane. And of course, this function is actually going to be more smooth than that. So it wasn't quite exactly the same thing, but we definitely got in the right direction. And the nice thing is, it will tell us not just the slope gradient, but also the bias gradient. And now we got both of these at the same time. So it actually says that it looks like changing the bias at this point would have more of an effect than changing the slope. So I'd still want to change the slope a little bit more, but I'd want to change the bias even a little bit more than that. So I can use these two to get us a descent direction. I could say that I want our slope to go down by slope grad and our bias to go down by bias grad. Now I'm going to need to use data, and I want to not, just because of PyTorch internals, and I'm going to also want to make sure that I don't step a huge amount in that direction. I'll just do some like 0.1 times that, and I'll do 0.1 times that. Now it's redundant to say the same thing twice. Let's call this learning rate, and I'll use learning rate here, and I'll say that the learning rate is 0.1. And now that should cause this error to go down even more. And great. So I'll pause here, and we'll come back and do the backpropagation part of this so we can figure out what PyTorch is doing under the hood.